your chemistry teacher, and today we are going to be discussing UV visible spectroscopy. UV visible spectroscopy, that is what we are going to be seeing today. The UV visible spectroscopy. UV visible spectroscopy, and today we are going to be concentrating on the principle. Let's look at the principle. And in subsequent classes, we're going to look at the instrumentation, and then we'll look at the application of the UV visible spectroscopy. Now, do not forget to share this class to your colleagues. Don't forget to also, important for you to share this class to your colleagues to be part of what we are doing. Don't also forget to like, don't forget to follow, don't forget to subscribe. And remember to tell them to subscribe so they can also get these videos as soon as they drop. Now, do not also forget that there is a Facebook page, Dr. B Chemistry Class or Dr. B Science Classes. And do not forget to also share to your colleagues and friends to be part of this. Do not forget to ask them to follow. Don't forget also to like and to comment. Thank you. Now we're going to look at what UV visible spectroscopy is all about. Interestingly, you should know that spectroscopy is just talking about how you can possibly measure certain wavelengths or measure certain absorbances or certain transmittance by simply looking at the nature to which materials absorb light from the electromagnetic spectrum line at particular wavelengths. Okay, so that is what spectroscopy is all about, and at the end of the day you are going to have a result that is detectable from a detector that will be a form of a spectrum. And that spectrum is where you can be able to characterize or identify certain molecules at the end of the day. That is what spectroscopy is all about, or spectrophotometer as the case may be. But what is the UV visible spectroscopy? Before we go into that, it's important for us to know that UV radiations are not visible radiations. You don't see UV radiations with your naked eyes, unlike the visible radiations. Okay, UV radiations are always radiations that find themselves around 200 to 400 nanometer in the electromagnetic spectrum. Alright, so these UV radiations are actually divided into three. So you have UVA, you also have UVB, you also have the UVC, and these are all rays. Okay, they are all radiations, and these UV radiations are all in the bands of 200. All of them are in the bands of between 200 to 400 nm, which of course is the nanometer measurement of radiations at the electromagnetic radiation spectrum. Now if we look at these radiations as being types of UV radiations that are not visible with the naked eyes, the UVA radiations are the radiations that you and I are feeling every day of our lives on Earth. UVA radiations are 95% UV radiations that reach the Earth, and a lot of these radiations are what causes wrinkling and also cause skin aging. All right, so these radiations always cause skin aging. They cause skin aging, and they also cause skin aging, and they also cause wrinkling. Okay, and a whole lot of what they cause. And these radiations are about 95% UV rays that reach the Earth. Like I said, whether they are UVA, B, or C, these radiations do not, the radiations actually cannot be seen with the naked eyes. But these radiations, as they are here, fall around 200, 400 nm at the electromagnetic spectrum. And these radiations are 95% UV rays that reaches the Earth, and these radiations contribute to skin aging and also contribute to what wrinkling that you find on your body, and a whole lot of them. Ordinarily, we must know that of course UV radiations are radiations that are likely to cancer formation. Okay, they are likened to cancer formation. So most of these radiations, UV radiations, has side effects. They form cancer, they cause wrinkling, skin aging, and a lot of them. But they have their own relevance. So the UVA radiations are radiations that reaches the 95% UV rays, while the UVB, UVC radiations are 5% UV radiations that are absorbed at the Earth atmosphere. Okay, so these ones are absorbed, these ones are absorbed at the atmosphere. They are absorbed at the atmosphere. So these radiations do not reach here. They are absorbed at the atmosphere, but the UVA radiations are the ones that we see every day, or rather we feel every day on the Earth. Okay, that is by the corner. But what is the UV visible spectroscopy? Now I want us to know that UV visible spectroscopy tries to measure radiations that are absorbed, UV radiations rather, that are absorbed, okay, by a substance, either absorbed by molecules, atoms, or ions, or substances, okay, and the radiations that causes excitation. Okay, now when these radiations are possibly absorbed, when UV radiations are absorbed by matter or by substance, by its ions, atoms, electrons, or even molecules, they simply do what? They simply cause them to vibrate. And when they cause the electrons to vibrate, the electrons will do what? Will excite. So there is an excitation from the ground state energy level, where you have the lowest energy level attainment, to the highest energy level attainment, which is the excited state. Usually there is both excitation and de-excitation in the process of the UV spectroscopy process. So the principle of UV spectroscopy is simply that when you have a substance, when you have matter or a substance, and you allow light, UV light, at a range of 200 to 400 nanometer to go through that particular substance, it is going to cause an excitation. It is going to cause first a vibration of the molecules of that substance, and then it is going to cause an excitation as the electrons or the particles of that particular material at the ground state energy level absorb the UV radiations and excite themselves into the higher energy level, where they will definitely do what? Give up light. Now when they give up light in the process of their excitation from the ground state level to the highest energy level, they are going to give up light, and that light is what you are going to measure as absorbance. And then as you measure that light as absorbance or even transmittance at the end of the day, that light will allow you to do what? To be able to do what? Make some calculations from the spectrum, and then the figures you have on the spectrum will give you opportunity to do what? To classify, to detect, and also to do what? Characterize certain molecules. That is just the principle that covers the UV visible spectroscopy. Now let us just put down something that will just guide us through. Now to put us something that will just guide us through, now let us look at this. Let's say we have this. So now if this of course is the ground level, is the ground energy level, or ground energy state, all right, and this of course is the excited energy state. Okay, so at this level we could have this, and we have this. Okay, we have this, we have this, we have this. Okay, at this point that we have here, what the principle says is that if the whole of this process we have here is matter or is a substance, that this substance will take in a UV visible light or energy, will take in a UV visible light or energy, and once it comes into the substance, which is this, the first thing it's going to do is going to cause a vibration in this substance. And when it causes a vibration in this substance, the electrons at the lowest or ground state energy level will do what? Absorb this visible light, this UV visible light into them. And once they absorb the light, there will be an agitation and a possible excitation of these particular electrons to this level. So it means that they are excited. Now once they are excited, they will do what? They will give out light. They will give out light. Okay, now you can possibly still have electron at this getting excited to the next energy level, or some can even excite across to, depending on the amount of UV visible light or energy that they can take in. Because the more energy that an electron or a substance can take, okay, the more the more excitation that you can get. Okay, so if this electron here has to acquire more energy, definitely it has a higher excitation. And this high excitation explains the fact that there is a shorter wavelength for this particular electron to do what? To move. Now the same thing happens in there. Here it means that this particular electron at the ground state energy level absorbs just a little of the UV radiation, so it's expected that it's not going to go too far. So the frequency or the wavelength, of course, is going to be quite longer. Now you can also have electron at this particular level of excitation, after being excited, drop back to what? To this particular ground state energy level. At this point, there is light that is given out, and even at this point there is light that is also given off. Okay, or given up. Okay, let me zoom on. So at this point there is light that is given out. At this point there is also light that is given out, as the case may be. Now these lights that are given up at this point, whether at the point of absorbance or at the point of transmittance, whether the light that are given up at the point of absorbance or at the point of transmittance, these lights are the reason why you have a spectrum that is being formed. And the spectrum that is being formed will always do what? Be based on absorbance and transmittance of energy. And this absorbance and transmittance of energy is what you relate to the wavelength. Okay, and when you relate that to the wavelength, you'll be able to get information that can allow you to do what? To characterize and identify molecules in various substances. Now that is the basic principle. But it's also important for you to know that there are 4 different types of transmission, okay, or transmittance. Okay, so it's not just about the fact that you can have electrons being light being transmitted because of electrons, falling from a higher energy level down to the lower energy level of ground state, or you can have absorbance of light from the ground state down to higher energy level. No, there are different types of transmission of light. Now, these different types of transmission of light are, we have the pi to anti-pi transmission. We have the N to anti-pi transmission. We have the sigma to anti-sigma transmission. We also have the N to anti-sigma transmission. So these are the different 4 types of transmission you can also have, or let's say excitations that you can also have, as the case may be. Now it means that this is the pi. Remember that for bonds, it is the bonds that you have that allow for these very excitations that you have. So for the different bonds that you have, some of them have pi bonds, some of them have sigma bonds. Now these are non-bonding. So you could have excitation from what? From the pi, okay, which of course is more like the more like the bonding, okay, to the anti-pi, which is the non-bonding. You can have the non-bonding itself down to the anti-pi. You can also have the sigma to the anti-sigma you can also have the non-bonding to the anti-sigma. Now, these are the different transitions or excitations rather that you can experience in a typical UV visible spectroscopy that leads to the information that you get at a detector, where you can be able to do what? To characterize, identify some molecules in substances. Now, there is an order to which this excitation is possible or transmission is possible. So there is a higher excitation found around the sigma to anti-sigma bond, and there is a further excitation greater to that of pi, and this is greater to that of n to pi. So this is the order to which this excitation can go through. So there is higher excitation at the sigma to sigma anti-sigma bonding, and there is also a non-bonding to anti-sigma bonding. So the higher, this will have a higher excitation compared to this. That's what it means. So whenever UV absorption comes in, those particular molecules or those particular substances that possess the sigma to anti-sigma bonding will always have higher excitations, and that means that you will have a longer excitation, and will also experience what a possible better wavelength for them. And then you can also easily be able to interpret and also to characterize the various molecules that they carry. Now, it is important for us to know that in this class today, we have been able to do justice to the principle of the UV visible spectroscopy. But before I go, I want to let you know that, again, the principle of the UV visible spectroscopy simply says that UV visible spectroscopy can be found only around radiations or electromagnetic radiations of about 200 to 400 nanometer. And it simply says that when you have a substance and that substance is placed on a sample cell or reference cell, that substance will acquire a UV radiation of that particular nanometer of 200 to 400 nm. And when it acquires that particular radiation, there is going to be a vibration in the substance internal structure. This vibration will allow those particular electrons at the lower energy level to absorb the UV radiations, get themselves excited to the next or the most highest energy level. And when that happens, there could also be a corresponding transmittance at the end of the day. So when that happens, there is absorbance, and then that absorbance is what is connected to the detector that will possibly give you signals which form a spectrum. And at the end of the day, you can use the spectrum because of the absorbance that is measured and correspondent with a correspondent wavelength, be able to get figures or data that can help you or can aid you to interpret or get you characterize or help you analyze or detect different types of molecules. Now, this is how the principle works. We are going to look at how the instrumentation of UV visible spectroscopy goes in our subsequent class. So do not forget to join, do not forget to share, do not forget to subscribe, so that when the instrumentation comes out, that class comes out, you will be able to find this class pop up in your phone, and then you can be able to follow us on the instrumentation of UV visible spectroscopy. Now, until next time, it is bye.